Today we will see how to compute the sample size for Poisson counts. So a Poisson count is a way to model counts. So for instance, let's say that you have a large population, so let's say 100,000 people, and then some event occurs to 1% to 0.1% of that population. Those are rare events, so are events that do not normally happen. This is the case of uncommon adverse effects of drugs. And then the probability of observing a given Poisson count, so let's say two adverse effects in these 100,000 population size is given by this formula. So the main parameter here is lambda. Lambda can be described as the mean count per unit, kind of what is the probability per person of having this adverse effect. Okay, so we will calculate this Poisson count in three scenarios. So in the first one, we will construct a confidence interval on the Poisson count. The second one, we will compare the Poisson count to a reference value. And for the third one, we will compare the Poisson counts or the Poisson means in two different samples. So the first case, that is constructing a confidence interval for the Poisson mean, let's say that we are interested in uncommon adverse effects, that we expect them to occur in 1% to 0.1% of the population. So you see that lambda here, that is the mean of the Poisson count, is a probability, and it is a probability of a very rare effect. And it is a rare effect if it is 1 to 0.1%, or on the contrary, if it is 99 or 99.9%. So in that case, what is the rare event is the opposite. So these are the tools to deal with probabilities in the extreme of the 0-1 range of probability. And we will construct we want to construct this Poisson count mean with a 10% of precision and a confidence level of 95%. So that means that our confidence interval should contain the true parameter with probability 95%. So yes, we have described the probability of observing k adverse effects in n individuals when the probability of each one of the individuals to show the adverse effect is lambda. Then on average we will expect n times lambda adverse effects is this one. So in our case, lambda is between 1% and 0.1%. So we have to calculate n for the worst case, which is the lowest probability, so the more rare event. So this is lambda 0.001, and because we want to have this 10% of precision, then lambda L has to be, so the lower bound and the upper bound, they have to be 0.9 times lambda and 1.1 times lambda. That give us these values. Okay, and just to show how the Poisson distribution looks like. So this mean is n times lambda in our notation, and then you see that if the mean is small, then the distribution looks rather skewed. When as the mean grows, the distribution looks more and more like a Gaussian. Actually, when n times lambda is sufficiently large, it can be well approximated by a Gaussian distribution. Okay, so to construct our confidence interval, we have to find n such that the probability from k prime to infinity when we have the lower bound is alpha half, so this is the lower bound, and then from this point to the from k prime to infinity is alpha half, and then for the upper bound, so that we have this distribution, the probability from 0 to k prime is also alpha half. So in this case, k prime is 400 and n is 400,000. So this may look a lot, but we have to take into account two considerations. The first one is that the events are very rare, so it is very unlikely. So in 1,000 people, we will see only one person in the worst case, so when lambda is 0.001, so in 1,000 people we will see one person. So, and it might be that we don't see anyone. So we would be in this regime where the mean is 1. So these are very rare events, and rare events require collecting a lot of events, many more than 1,000, to be able to be sure about what you are saying. The second effect is that we want it to be very precise. So this 10% of maximum error in the upper and lower bounds, it is a very strict constraint. So that means that you will need a lot of individuals for that. So this is the exact solution, and the exact solution, you can imagine that with equations like these, it is not simple to solve for k prime and n. Okay, we can approximate the Poisson by a Gaussian when n times lambda, that is the mean value of how many you expect to have, how many observations you expect to have, is larger than 30. And then if it is larger than 30, then this new variable x minus the mean divided by the square root of x is distributed as a normal 0,1 variable, and then we can use all the Gaussian machinery to compute confidence intervals and to compute sample sizes, and we recognize the traditional formula, so a term that depends on the confidence level of the confidence interval, and then the normalized effect size. So here delta, remind, it is the allowed percentage of variation of lambda. So we see that it is not exactly the same number that we had before, so it is a little bit larger, but it is in the same order of magnitude. So it is, I don't know, 2-3% of difference. Okay, so also there is another transformation that is called the square root transformation. That is this one. The square root of x is distributed also as a Gaussian with this distribution, and from here we made it use also the sample size in a different way, and this is the different way. And again, in our case, we have a number that is also around 400,000. In this particular case, this estimate is a bit more accurate than the previous one. Okay, so that is if you want to construct a confidence interval. If you want to do a test, then you will compare the Poisson mean to some, or the event rate to some reference value. So for instance, we want to detect whether an adverse effect is uncommon, and uncommon is less than 1%, or common, that is more than 1%. How many individuals do we need to study, and how many adverse effects do we need to observe to decide So for instance, we want to have a power of 90% if the probability of these adverse effects is larger than 2%. So we have a reference value that will be the 1%, and then if it goes beyond 2%, then we already want to have a statistical power of 90%. So you may recognize here the kind of reasoning that we have been following all the time. So we have to find a point k prime, this is the critical value, such that if the null hypothesis is true, from that point to the right we have, or from that point to the left we have 1 minus alpha. It is the same as saying from one point to the right we have alpha, and then from that point to the left we have beta. So here we have this, that representation. So we have the null hypothesis. From this critical value to the left, to the right we have alpha. From the alternative to the left we have beta. And in this particular case we have to study 1300 people, and k prime, the critical value, is 19. So that means that we have to study 1300 individuals. If more than 19 have adverse effect, then we will reject the hypothesis that the effect is uncommon, and we will accept that it is common or very common. Okay, and as we did before, we don't need to solve these complicated equations involving the Poisson count. We may use the Gaussian approximations. So for instance, if we use this one, that is used when n times lambda is large, then the sample size, which we have as the typical Gaussian formula, so the term depending on the confidence interval, on the confidence level, the term depending on the statistical power, and the normalized effect size. And in this case we see it is pretty similar, so it is 1700 as opposed to 1300, so in the same order of magnitude. And what if we want to compute, we are not comparing to a reference value, but we want to compute the difference between two Poisson means or rates. Okay, so let's say that there is a disease, tuberculosis, that in Brazilian prisons is 20 times larger than in the general population, and it is about 1%. So in the prisons it is 1%, outside the prisons it is 1% divided by 20. We want to determine whether this larger prevalence is larger in male prisons or in female prisons, and we want to have a power of 90% when the difference is larger than 0.5%. Okay, so now we will have two Poisson rates. We will have lambda 1, lambda 2, and we want to determine whether lambda 1 is smaller than lambda 2. Lambda 1 would be female prisons, and lambda 2 male prisons. And we want to have let's say that in female prisons it is 1%, and we want to see if lambda 2 is larger than 1.5%. Okay, so again the exact calculation can become rather complicated. So we define this probability depending on x1, x2, and 1 and 2. So n1 and n2 are the sample sizes in each one of the groups. x1 and x2 are the number of observed events. We define this probability as the binomial of these parameters, and then the probability so this probability is the sum of the binomial between 0 and x1 when the binomials have this distribution, these probabilities here, and then yeah, there is a mistake here. That shouldn't be this smaller than or equal alpha. And then we have the indicator function. We have this. If this value is smaller than alpha, then the indicator function takes value 1, and then we multiply these Poisson probabilities x1 of observing x1, and this is the mean, and observing x2 when this is the mean smaller than beta. So we want all these to be smaller than beta. So we see that we have an equation that somehow depends on the confidence level and also depends on the statistical power. So it is a rather complicated design. And then the solution, in this case with this data, that in female prisons it is 1%, in male prisons it is 1.5%, and these are the confidence level and the statistical power. Then we have x1 is equal 120, x2 is 101, and we have to study about 10,000 people, a little bit less in N2, but about 10,000 people in each one of the prisons. So how to read these? We will study N1 female and N2 male prisoners. If we observe 120, this is x1, female prisoners with tuberculosis and more than 101 male ones, we would reject the hypothesis that lambda 1 is larger or equal to lambda 2. That is this one. Okay, and again we look for approximated methods, because otherwise the design becomes too complicated. So we may transform this into this other hypothesis test. This is simply taking lambda 2 to the other side, and if the Poisson counts x1 and x2 are large, then this ratio here is distributed as a normal 0, 1, and this variance is defined in this way, where R is the ratio between N1 and N2, the optimal allocation, so the one giving the minimum sample size for the combination of the two groups is given by the ratio between lambda 2 and lambda 1. So under this method we can compute the sample size, and we have the typical Gaussian formula, so the confidence level term, the statistical power, and then the normalized effect size. And yeah, with the optimal allocation of R equal this one, lambda 2 divided by lambda 1, that is 1.5, we have 10,000 for one of the groups, 7,000 for the other group. That is approximately what we had here. So we had 11 and 7,000, so it is almost there. And this is a different approximation. So if n1 lambda 1 and n2 lambda 2 are large, then this difference normalized in this way is normalized in the 0, 1 way, and these are the formulas for the sample sizes. And again we get something like 11,000, 7,000. So we see that approximate methods are pretty good if the conditions are met. Yeah, even yet another approximation, and again values in the same range. And we can have a correction for background counts. So there are some processes like radioactivity counts that may have a common background count that is lambda 0. So in one of the groups you have lambda 0 plus lambda 1, and in the other group you have lambda 0 plus lambda 2. So the number, in this case, the number of samples needed is modified. And for instance, in the following the square root transformation, we would have these formulas for the sample sizes, and the optimal allocations are given by this thing. Okay, so in summary, The exact formulas related to the Poisson counts are rather complicated. There are approximate formulas and also the unbalanced allocation, so having more samples in the group where the events are more rare reduces the total sample size. And here is an example of these formulas. So we have the term depending on the confidence level, the term depending on the statistical power, and then a normalized effect size. And the normalization depends on what is the transformation that we have used. So this would be all for Poisson rates, and see you in the next video.